Okay, almost through the AP Physics 2 Unit 3 Lesson A multiple choice. This is the last part, Part 4. A handful of them here, a little more. So let's get started. Three objects, X, Y, and Z, are each given an excess electric charge. The objects are then brought near each other in pairs, but do not touch. It is found that X and Y attract each other, and Y and Z repel. And X and Z attract. Which of the following is a correct conclusion about the signs of the charges that can be drawn from these observations? That's a good question. So, just going on, we're assuming that charge can't move around or that polarization isn't an issue. So if we're just taking it at face value, you could say that X and Y, if they attract, they're going to be opposite signs. Y and Z repel, they're the same. X and Z attract. So if X attracts with Z and X attracts with Y, I would assume Y and Z are the same, which is why they would repel. Okay. So I would say that Z and Y have the same charge, have the same sign. We don't know which. So I would say Y and Z have the same charge, and and X has the opposite. I would go with C as my answer, and I believe I'm right. It's not my favorite question in the world because if they're conductors, I don't know. I'll let it go. But C is the right answer based on what they got there. 2-point charges of unknown magnitudes, Q1 and Q2, are placed as shown above. The electric field intensity is 0 at point P, which is closer to Q than Q2. Sorry, Q1 than it is to Q2. Which is following is true about the signs of the charges and their magnitude. Well, in order to be 0 here, we'll call this one the green. Either the green has to point this way and the red has to point this way, or vice versa. Let's just go with this scenario. If this is the case, that would make this negative and make this negative, because it would both be attractive. Or, if I reverse the directions, it would both be positive, but they've got to be the same sign. If they're different signs, then they would point in the same direction in between them like this. So I would say they're the same sign. So we're down to C, D, and E. And the bigger charge has to be Q, because it's farther away and is still able to match Q1. So Q2 should have the bigger charge. Q1 is less than Q. I would go with E in this case. What is the acceleration of an object of mass, okay, with a charge of this, under the influence of an electric field of this? Okay, so interesting question. So what you need to know first from this is force. Electric force is an electric field strength times Q. So the force comes from this times the charge. So that's going to be electric field strength is 5,000. This is a charge of 9 times 10 to the negative 9th coulombs. So I get 5,000 times 9e negative 9. Alright, and I get a force of 4.5 times 10 to the negative 1, 2, 3, 4, 5 times 10 to the negative 5th newtons. Now I go to, that's the only force, that is the net force. Therefore, that force divided by the mass of the object will give me the acceleration of the object. So it's going to be 4.5 times 10 to the negative 5th newtons. Newton's second law says if I divide by the mass, 4.5 times 10 to the negative 5th kilograms, how convenient, comes out to be 1 meters per second squared. So, whammo. So a combination of knowing how electric force in this case is generated by multiplying E times the charge, and then applying Newton's second law to that force and that mass. Alright, so there's a couple questions here, 56 and 57. Charges Q, negative Q and positive Q are located on the X and Y axes respectively, each at a distance d from the origin. What is the direction of the electric field at the origin? So, I've done this a few times. Red. If you do all the multiple choice, you should start getting the feeling like, I've done this problem before. And that's fine. You could even skip. If you got to this problem, you got to that point, you'd be like, I can figure it out. You want to skip it? That's fine. If you want to do it just to reinforce, it shouldn't take you too long. So, if I'm at the origin, the blue is going to attract me this way, and the red is going to repel me this way. If I'm a little positive test charge at this location, that means the net field is going to be down and to the right. I would go with D in this case. Now, scrolling down, 57. What is the magnitude of that? Well, what do they want? The electric field. So this is going to be, say, they're both going to be the same magnitude, the individual ones, and that's going to be K, Q divided by D squared. There's two of them, but they add as Pythagorean's theorem, so it's going to be the square root of KQ over D squared squared plus KQ over D squared squared. So there's two of them. Then we can take the square root. So it's going to be the square root of 2 times KQ over D squared. So I'm looking at D for this one as well. Which of the following is true about the net force of an uncharged conducting sphere in a uniform electric field? Net force should be 0. All the negatives that are on it would be pushed one way, the positives would be pulled the other. So it would be 0. If it had a net charge on it, then yes, there would be a force. But in this case, it's uncharged, so for every positive that ends up on one side of the sphere, a negative will end up on the other, pulling the other way, pushing the other way. So, all right, I think that's it.